Now we're looking at systems of linear equations in three variables.
So as you recall, a system of equations, you must have the same number of equations as you do variables in order to solve the system. So with a system of three variables, linear system, we're going to have three variables and three equations. So a linear system in three variables is like finding where three sheets of paper meet. Okay, you've got three planes. There are three types of solutions. The first thing we could have is a single point. So notice down here, if all of those sheets of paper kind of cross in a way where they meet in one point, then we have one single solution. And notice it's given not as an ordered pair, but like an ordered triplet in alphabetical order, the X, the Y, and then the Z. It's also possible to have infinite points, but unlike two linear equations, when we've got planes, those infinite points come along in a line like this, okay? So we're going to write one of the variables as just the variable, but the other two variables in terms of that one variable. I know that seems like a lot, but we'll do an example so you can see it here in a minute. Third possibility is no solution. The example on the very right, you have three planes all parallel to each other, so none of them cross anywhere. But it's also possible for maybe two of them to cross at a time, but there's not one place where all three of them meet. In other words, it has to be a solution for all three, not just two. And remember, points represent solutions to the equations. Equations are represented by those points. So let's do an example of a single point solution. This is what we call a consistent system. So in equation 1, we have 3x minus 2y plus z equals 2. Let's call that equation A. Then 5x plus y minus 2z equals 1. Call that equation B. And 4x minus 3y plus 3z equals 7. We'll call that equation C. Now we're still going to use substitution or elimination methods like we've learned before. It's just we can only work with two equations at a time. So here's our goal. We're going to reduce it from three variables, three equations, down to two variables, two equations, down to one variable and one equation. Okay, so let's first get it down to two equations with two variables. So let's pick any two equations and get rid of one of our variables. A nice one might be, to get rid of the y, we can choose A and B. So notice equation A has a negative 2y. So we're going to write it as is, 3x minus 2y plus z equals 2. But if I want to eliminate the y there in B, I need to multiply equation B by a positive 2. So that would give us a 10x plus a 2y minus a 4z equals 2. Now we can combine these two equations and come up with a new equation. We'll call it equation D. That gives us a 13x, the y's are gone, minus a 3z equals 4. So now I have one equation with two variables. I need to come up with another equation with the same two variables, which means I need to choose a different pair, either A and C or B and C, and then come up with another equation where I've eliminated the y. So since the B already has a single y with it, why don't we use the B again? But this time, since we're trying to get rid of the C, we're going to multiply equation B by 3. So that will give us a 15x plus a 3y minus a 6z equals 3. And we'll leave C as it is, 4x minus 3y plus a 3z equals 7. So when we add these two equations together, we'll call that result equation E. We get 19x, our y's add up to 0, minus 3z equals 10. So now we've taken our 3 equations with 3 unknowns and we've whittled it down to 2 equations, 2 unknowns. So I'm going to take this E and I'm going to write it here underneath my D just so I can compare apples with apples. 13x, I have a negative 3z equals 10. And now we have to eliminate again to get it down to 1 variable, 1 equation. Well, it looks like the z's would be a good choice. So I need to take one of those equations and multiply them by a negative. So I'm going to multiply, let's say, equation E by a negative 1. So that will give me a negative 19, a positive 3z, and a negative 10. So when I combine those equations, we now have a negative 6x. Our z's add up to 0, equaling a negative 6. So when we divide both sides by negative 6, we get x equals a positive 1. So notice how we whittled it down. In blue, we still had 3 equations, 3 unknowns. Our resulting equations in green, we had 2 equations with the same 2 unknowns. So notice both blues, I got rid of the y's. If we'd gotten rid of the z's the first time, we'd had to get rid of the z's the second time. Be consistent. Matter of fact, write yourself a note. Must eliminate same variable. So now that we have x equals 1, we have one of our solutions. We are going to plug this into equation either D or E and solve. In other words, we're going to create another equation with only 1 unknown. So we can choose equation D. Equation D is 13x minus 3z equals 4. We're going to plug in 1 for x. So when we solve for z, we get z equals a positive 3. And now we have to find our y. So we're going to backtrack again and plug everybody into one of our original equations. So if we choose equation A of 3x minus 2y plus z equals 2, we're going to plug in the 1 for the x. We still have a negative 2y. We're going to plug in a positive 3 for our z and solve. So we end up with the solution of 1 point of 1, 2, 3. Again, x, y, z, we always put it in alphabetical order.